Hello, ladies and gentlemen. I hope you're all doing well. Root Beer here, looking at our sixth question from the 2010 Euclid contest. So, light bulb question part A. A snail shell is formed from 6 triangular sections as shown. I'm noticing a bunch of right angles, and I'm noticing a bunch of 30 degrees, so I'm gleeful because these are going to be 30, 60, 90 triangles. Oh, and they even go on to tell me each triangle has interior angles of 30, 60, 90. I should really read the rest of the question before I get excited that I've noticed something. If AB has a length of 1, what is the length of AH? Okay. Okay. So, the nice thing about 30, 60, 90 triangles is because they're similar triangles, what you really need to know is the ratio of the sides. That way, if you know one side length, you know all the side lengths. So if we've got a 1 here, and we don't have a 1 here in this question, it's actually opposite the 60. But if you have a 1 here, you'll get root 3 here and a 2 here. So if I had x down here, this side length is 3 times x, and this side length is 2 times x. And you can rearrange this as you need to. If you're given the hypotenuse, you can figure out the other 2 sides. If you're given the root 3, the one opposite the 60, you can figure out the other sides just as well, but with nice ratios. But it's a very, very common triangle to come up on contests, and so it is something to be aware of and to not even have to think about. Just 1 to root 3 to 2 is the ratio. Okay, so we'll draw a little bit of our picture. I think it actually goes a full, because there's 6 of them, all making 30 degrees from the center, so it is a straight line. 2, 4. There we go. It doesn't have to be exact. I see people getting out their protractors and things on contests. You don't have to. As long as your picture is roughly as you are describing it, or roughly corresponds to the things that you want to achieve, then that's good enough. You don't have to measure it out 3 centimeters exactly or anything like that. So, I'm going to use orange to mark off our 60 degree sides, or 60 degree angles. And let's say blue is our 30 degrees, and all the 30 degrees are on the inside. And A was our center, and it was A, B, and then I think we just went C, D, E, F, G, H. Okay. So AB is 1, but in the context of our 30, 60, 90 triangle, this side's x, this is the root 3x, and this is 2x. So AC is going to be, well, it's 2x. And that's going to be 2 divided by root 3 times root 3x, which is 2 root 3 times our AB. Okay. So that's how we can figure out AC. But once I know AC, and we're trying to work our way around to AH, and I think it's just quite natural to follow the triangles as they get bigger. Once we're in the ACD triangle, well, again, 30, 60, 90, so we have a root y, but now, or a y, but now we've got root 3y here and 2y. Now we can go through the same calculation here. If it were a written question, we'd have to, and then maybe make a generalizing statement, but it's a light bulb question. So we can really just say, well, you do the same thing to get from AC to AD as you did from AB to AC. So AD is 2 over root 3 times 2 over root 3 AB, because that's what AC was. And AB is 1, so, I mean, you could substitute 1 in there if you want to. But it's going to be the same thing. AE, you multiply by 2 over root 3 again. AF, once again, AG, and finally AH. So AH is going to be 2 over root 3 how many times? Well, it's to the power of 0 if we're at AB, because you don't actually multiply it. We multiplied by it once with AC. We had 2 copies, 1, 2, when we did AD, so 3, 4, 5, 6. So to the power of 6 times AB, but that's equal to 1. So this is 2 to the 6 over root 3 to the 6. 64 over 27. And there we go. So that's really the answer you need, is just the 64 over 27, but we have shown our work. It's not really in full sentences, but the pictures are there, and the continuing of the same multiplication, I think, is adequately represented. But I'm confident in our answer. Okay, 6b now. Big old written question. In rectangle ABCD, point E is on the side DC. Line segments AE and BD are perpendicular and intersect at F. AF is 4, DF is 2. Determine the area of the quadrilateral. Oh, I remember this one. Okay. So I've mentioned this before, but I help out at a local enrichment program, and one of the things we try and get them to do is be prepared for the Euclid. So I was filling in for someone. I don't usually do the Euclid stuff, at least not the last few years. But I was filling in for him, and I think we were doing this contest a month or two ago. And I don't just try and do the solutions, because I got people there, so we have a back and forth, which unfortunately we can't really have on the internet, and I do apologize for that, because I'm so much more charming in person. But I was trying to say, okay, and then what would you do? And what would you do? And we got to question 6, and the students, they saw the right angles, and they just went nuts for the Pythagorean theorem. And I get the sense, because just about every kid in the room was saying, oh, you Pythagorean theorem, call this x, call this y, you'll get this equation, this equation, this equation, you can put them together, and they were approaching the right answer. But my goodness, it was going to take them a long time, and while the Pythagorean theorem is great, and while algebra skills are fantastic, there is a better way to do this question. I don't want to embarrass myself and have this not be the question, but I'm pretty sure it's the same question I'm thinking of. You can do this with similar triangles, and it's just so much cleaner because it's just single ratios, and this ratio is equal to this ratio, and this I think going to be a little bit of Pythagoras at the end, but don't just jump to algebra because you know it'll work. Take a step back and say, well, this is a geometry question. There are other ways to handle things. That said, okay, that said, if you know a way to do a question and you know it's going to get you there, get you the answer, you do it. You go for it. But I would encourage you to maybe make a little bit of a pause and say, okay, that's one way. That's going to involve a lot of work. Is there a nicer way? And a lot of times you'll just say, no. But in this case, the similar triangles are actually going to help a great deal. And I'm going to try and go through that way. All right, now, so let's get a copy of our picture written down. So we have this diagonal, and then we chop it right there. You get a nice little right angle there. And we have a 4 and a 2, and it was what? A, B, C, D, F was here, and I think this was E. Let's just double check. Okay, everything's good. And we got 4 and 2. Okay, now we can use, and this is a written question, so we should explain. So by Pythagoras, AD is the square root of 4 squared plus 2 squared. So it'll be square root of 20, take out a factor of 4, so you'll get 2 root 5. Okay, so 2 root 5 here. And here's where the similar triangles come in. Just very briefly, people were trying to say things like, well, you let this be x and this be y and other things like that. And it's, you can set up equations. There's a lot of right angle triangles to work with here. Now, intersecting lines, so you're gonna have a right angle over here, and then making up 180, we'll get right angles everywhere. So there's lots of right angle triangles, and you should probably mention that at some point, that we get all of these. But more than that, let's just take a look here. We've got an angle here. Now, this angle and the angle down here in the rest of the triangle add up to 90 degrees. And so we're going to get an x here. And we're going to get the dot angle here. And similarly, we make up a 90 degree here. X and dot add up to 90. So we'll get a dot here and an x here. And so we have a bunch of similar triangles. So you would say something like, we notice, and you can cite the angles as you're showing that they're equal, but we notice that triangle ADF is similar to triangle BAF. Got to keep the order right. And then triangle, so I'm doing the one at the dot first, then the one at the X, so we'll have triangle DEF. Okay. Now we want the area of this quadrilateral. Well, this quadrilateral is sort of the big right angle triangle in the bottom minus this smaller right angle triangle. And if we check the big right angle triangle, is also similar. So we'll add that to our list as well. So that's similar to, we do dot first, then the one with the X, and then the right angle. Okay. So, what can we say? AB is going to be, well, AB over DA has the same ratio as AF over DF. This is why we keep the order right, so I can just sort of read these things off. Technically, I guess it should be BA over AD, but that's okay. So I don't know what BA is, but I do know these other ones. So BA over 2 root 5 is the same as 4 over 2, which is 2. So BA is going to be 4 root 5, and so is DC. So now I have a side of the big right angle triangle. Okay, so what else can we figure out from there? Well, if I know DC, DC is the one opposite the X, so DC over AF is going to be the same as BC. So that's the one opposite the dot, so that's BC over DF. And so that's 4 root 5 over 4. Oh, wait, no. Well, that is true. I don't need that. I just realized it's going to be 2 root 5. Why is it going to be 2 root 5? Because it's a rectangle and it's AD. So we'll just write that. So DA equals BC, as it is a rectangle. So the last thing we need to deal with is that smaller, the smallest of the right angle triangles. This one here, he's what we're he's what we're going to take away to figure out the quadrilateral. So we need to say something like FE. FE. That's opposite the dot. So FE to DF. So DF over FE is the same as, let's see, we know DF. DF to FE is the same as AF to DF. Right? Yeah, it's a nice little geometric sequence. So AF over DF, and that tells me, I guess, let's write it the other way, so that I don't have to do any reciprocal stuff. But we're going to get FE is going to be 2 squared over 4, so it's 1. Okay. Basically, the legs of our right angle triangles are in the ratio of 1 to 2, so we can actually figure out that this is 8, not that we need it. So we get a 1 here, we've got 4 root 5, we've got 2 root 5, so finally, quadrilateral of BCEF is triangle BCD minus triangle DFE. The area of the triangle, 1/2 base times height. and then 1/2 base times height. So the half and the 2 will cancel out, the half and the 2 will cancel out. We'll be left with 4 root 5 times root 5. So that's going to be 20 minus 1. 19 is the area of our quadrilateral. Okay. So that's it. It takes up most of the shape, actually, because with 2 root 5 and 4 root 5, the whole rectangle is 40. But that quadrilateral looks pretty big, I guess. Yeah, it all works out. The diagrams are never drawn to scale, but I do sometimes try and read into them a little bit. Anyways, that's question number 6. So up next, question number 7. I will see you for that in the next video.